Welcome back to reactions. This is part 4 of this unit and our last video on redox reactions. This time we are going to be balancing redox reactions using the half reaction method. Let's go. So I've got a whole bunch of rules here for how to balance redox reactions. It's going to look like a lot. We'll go through it to start with, but then we'll go through it step by step. So when you're balancing redox reactions, it'll have to tell you whether it's acidic or basic. First thing you're going to do is remove any spectator ions and separate into half reactions, so you're looking at just the things that are reacting. You'll balance all the atoms except hydrogen and oxygen, and then oxygen by adding water, hydrogen by adding H pluses, and then charge by adding electrons. Then we're going to multiply oxidation and reduction half reactions by some number to equalize the number of electrons, and then add them together. The atoms and charge should be balanced, and there should be no electrons left. When it's a basic solution, you do the exact same steps, except after adding hydrogen, add more hydroxide ions equal to the hydrogen on both sides so that they form water, leaving hydroxide left over. I know that seems like a lot, but let's do it step by step. First example. We've got NO3 minus plus Bi turns into Bi plus 3 plus NO2, that's bismuth. So, for acidic solutions, because we have an acidic environment, our first step is to remove spectator ions. Check, that's been done for us, and separate into half reactions. So, half reactions, remember, look at the oxidation number and see how it's changing. So, for bismuth, that's pretty easy. It's going from Bi0 to Bi plus 3. For the other, for nitrogen and oxygen, here we've got the entire compound nitrate is -1. Oxygen, remember, is -2 times 3 is -6, so hydrogen's got to be plus 5 in nitrate. Over on the right-hand side, the entire compound NO2 is equal to 0. Oxygen is -2, and there's 2 of them, so that's a total of -4. So nitrogen has to be plus 4 in order for the charges to balance out. So there's my oxidation numbers. Now I can determine who's being oxidized and who's being reduced. Let's start with oxidation, because the paper starts with oxidation. Oxidation is loss of electrons gained in charge. Oxidation is loss of electrons gained in charge. That's bismuth. Bismuth is being oxidized because it's going from Bi0 to Bi plus 3, or Bi3 plus. So, I've separated into half reactions. I know the bismuth is the first one. And for that one, I can just add 3 electrons. This is exactly like the half reactions we were previously doing. For reduction, it'll be a little trickier. Notice here that nitrogen is the thing being reduced, not oxygen. Oxygen is the same. But since it's within a covalent compound, the oxygen can't just be pulled away from the nitrogen. So for my reduction half reaction, it has to include the oxygen, even though the oxygen itself is not the thing who's being reduced. So, separate into half reactions done. Balance all atoms except hydrogen and oxygen. So, I've got NO3 on the left, NO2 on the right. They both have 1 nitrogen. I'm good here. So now part C says, balance the oxygen by adding water. My oxidation reaction is done. I'm just looking at reduction. So for NO3, there's 3 oxygens on the left. For NO2, there's 2 oxygens on the right. So I'm going to add 1 water molecule on the right so that I get 1 oxygen. Then balance hydrogen by adding H+. Since I put 2 hydrogens on the product side, I will need 2 H pluses on the reactants side in order to balance the hydrogens. So now I've got 2 H's, 2 H's, 1 nitrogen, 1 nitrogen, 3 oxygens, 2 plus 1 is 3 oxygens. So all of the atoms are balanced here in this reduction half reaction. All I've got left is electrons in this reduction half reaction. So look at the charges. 2 pluses plus a minus, that's a total of plus 1 on the left-hand side. And I've got 0 plus 0, which is a total of 0 on the right-hand side. In order to get the charge on the left equal the charge on the right, I'll need to add electrons to the reactant side, specifically only 1 electron, because if I add another 1 minus here, then this whole thing will become 0, and then the zeros will balance. So now my charges are balanced by adding electrons. Everything on this reduction half reaction is now balanced. So now that everything's balanced, let's go on to the next step. multiply to equalize the number of electrons. Notice that there's 1 electron on the left in the reduction reaction, 3 electrons on the right on the oxidation reaction. So we're actually going to multiply the entire reduction reaction by 3 so that we can have the electrons cancel out. So now that I've done that, multiply everything on the reduction by 3. That way these 3 electrons will cancel with those 3 electrons, so that for my final equation, I can just add them together. Everything on the left stays on the left. That would be a bismuth plus 6 H pluses and 3 nitrates. And then everything on the right stays on the right. That's Bi3 plus 3 nitrogen dioxides and 3 waters. To check and make sure I've done it all correctly, the atoms and the charge should be balanced. There should be no electrons in the final equation. So if I go back through, 1 bismuth on the left, 1 bismuth on the right. 6 hydrogens, 6 hydrogens, 3 nitrogens, 3 nitrogens, 3 oxygens, 2 plus 1 is 3 oxygens. The atoms are balanced. For charges, let me get rid of these green lines. For charges, I've got 6 pluses and 3 minuses on the left. That's a total of 3 plus on the left. On the right, I have 3 plus. That's a total of 3 plus on the right. Because the charge on the left and the right are the same, then this equation is balanced. Yay! We did it. Let's try another. All right. This one's not giving us any guidance. Doesn't even say oxidation reduction, but we're going to be able to do it. Start with the oxidation numbers. SO3 minus 2 means the entire compound, or ion in this case, is negative 2. Oxygen itself is also negative 2, coincidentally. Since there's 3 of them, that's negative 6. So sulfur has to be plus 4. Within IO3 minus, the entire ion is negative 1. Oxygen is negative 2, but there's 3 of them, so that's negative 6, which means iodine has to be plus 5. Aren't you glad you paid attention in that determining oxidation numbers video? For I2, by itself, 0. For sulfate, hey, we've done this one a bunch of times. The entire ion itself is negative 2. Oxygen is coincidentally also negative 2, which is negative 8, so sulfur is positive 6. Now that we've got the oxidation numbers assigned, we can figure out who's being oxidized and who's being reduced. So I see sulfur is a plus 4 and sulfur is a plus 6. Oxygen is a negative 2 on the left and a negative 2 on the right. Hey, that means oxygen is not part of my reaction. And then iodine is plus 5 on the left and iodine is 0 on the right. So the substance being oxidized for the oxidation half reaction, oxidation is loss of electrons, gain in charge. Gain in charge, that's going to be the sulfur. Starts as sulfur in SO3 minus 2, ends as sulfur in SO4 minus 2, which means that the reduction half reaction, I'll color that guy blue, has got to be the iodine. That's iodine in IO3 minus on the left and iodine in I2 minus on the right. So let's get started with our step-by-step how to balance. First thing, get rid of the spectators. Oxygen, even though its charge is not changing, is not technically a spectator because it is within these covalent compounds. So leave oxygen where it is. Then we're going to balance all atoms that are not oxygen and hydrogen. So sulfur, for example, I've got 1 sulfur on the left, 1 sulfur on the right. The sulfurs are good. For iodines, on the other hand, there's 2 iodines on the left, which means I have to have 2 IO3 minuses on the right. Now we're going to balance oxygens by adding water. On the oxidation half reaction, we have 3 oxygens and 4 on the product side. So we're going to add a water to the left, just for 1 oxygen. For the reduction half reaction, remember I had 2 iodates, so 2 iodines. That gives me 6 oxygens, so I'll need 6 waters. And now the oxygens are balanced. My next step is to balance hydrogens by adding hydrogen. For the oxidation reaction, I had 2 H's for H2. So then on the product side, I'll add 2 H's. This is H plus specifically, not plain hydrogen. That's because it's in an acidic environment, so there's H plus left over. For the reduction half reaction, 6 waters gives me 12 hydrogens. So there's 12, let's see, try that again, 12 H plus. So 12 hydrogens and 12 hydrogens. Now all I have to do is add the electrons to get the half reactions balanced. Let's look at a cleaner page. So here's the reactions I already had. The hydrogens, the oxygens, the sulfurs, the iodines. Everything's balanced except for the electrons. So let's go for the electrons. We have a total charge on the left of -2. A total charge on the right of -2 plus 2, which is 0. So in order to get -2 to be equal to 0, I'm going to have to add 2 electrons to the right-hand side, so that the right-hand side equals -2 to balance with the left-hand side -2. So 2 electrons on that top reaction. For the bottom reaction, I've got 12 pluses and 2 minuses. That's a total of 10 pluses on the reactant side. On the product side, nothing, nada. So how am I going to get 10 plus to equal 0? Well, if I added the 10 electrons on the product side, first of all, my electrons would be on the products for both of them, and that'd be automatically wrong. But I'd have 10 negatives over here and 10 positives on the other, which is not the same thing. I need them to be the same charge on both sides. So my 10 electrons are all going to go on the reactants side here. Let me clean this mess off and add in those 10 electrons. So next thing is to multiply whichever reaction in order to get the electrons to cancel. So the top reaction is going to multiply by 5. If I multiply the top reaction by 5, I'll get 10 electrons to cancel with my 10 electrons, and all will be well. So let me distribute that 5 everywhere I can find a place to do so. That should be 5 waters, 5 SO3s, 5 SO4s, 10 H pluses, and 10 E minuses. Now I've got my electrons canceling. Now I can add the 2 half reactions together. When you add the half reactions together, everything on the left stays on the left. So I've got 5 waters and 5 SO3 minus 2 and 12 hydrogens. Let's see if I can make that a nice plus there. And 2 iodates. All of that's on the left. For the right, everything on the right stays on the right. So this is 5 sulfates and 10 hydrogens and an iodine and 6 waters. Problem is, maybe you're noticing, there are still things that cancel, and so I'm still going to have to cancel those things. I see that there's 5 waters on the left and 6 waters on the right in my final reaction, which means all 5 of these waters can cancel out, and 5 out of 6 of those waters can cancel out. For my hydrogens, same thing. I've got 12 on the left, 10 on the right. All 10 of these can go, and all but 2 of these can go. That way everything cancels that you see on both sides. Now we're going to rewrite the reaction. Everything on the left stays on the left. So this is 5 sulfites, only 2 hydrogens, and 2 iodates. Everything on the right stays on the right. So this is 5 sulfates, no hydrogens, an iodine, and only 1 water. If you look back at your overall reaction, it should balance. 5 sulfurs, 5 sulfurs. 5 times 3, which is 15, plus 2 times 3, which is 6. So 15 and 6 is 21 oxygens on the left, 5 times 4 is 20, plus 1 is 21 oxygens on the right. 2 hydrogens on the left, 2 hydrogens on the right, 2 iodines on the left, 2 iodines on the right. All of my atoms are balanced. Yay! For charge, I've got 5 negative 2s. That's a total of negative 10, plus 2 pluses and 2 minuses. Oh, that's minus. All of that on the left, so the left is a total of negative 10. For the right, I've got 5 times negative 2, which is negative 10. Hey, check it out. Negative 10 does equal negative 10. This is a balanced equation. Yay! Let's do one in a basic environment. So here's our last example. This one's in a basic environment, so we're doing the exact same thing all the way up to the very last step. And then at the very last step, we're going to add in one more step because, there's not enough steps already. So, first thing is determine the oxidation numbers of everything. Oxygen is negative 2. The entire permanganate is negative 1. Since there's 4 oxygens, that's negative 8. So manganese is plus 7. Sulfite is negative 2. Oxygen is negative 2, but since there's 3 of them, that's negative 6. Sulfur's got to be plus 4 in this case. Sulfate has a charge of negative 2. Oxygen is coincidentally also negative 2. There's 4 of them, so that's negative 8. Sulfur, in this case, is positive 6. And in manganese dioxide, oxygen is negative 2. There are a total of 2 of them, that's negative 4. So manganese has to be plus 4. All my oxidation numbers are accounted for. Now I just need to figure out who's being oxidized and who's being reduced. Let's start with oxidation, because why not? So for oxidation, loss of electrons, gain in charge. Gain in charge, that's going to be the sulfur. Sulfur is the one being oxidized here because it's starting at a plus 4 and ending at a plus 6. So I have SO3 minus 2 turning into SO4 minus 2. So let's just do this entire oxidation reaction before we get to the reduction. Let's just see what we can do here. First I'm going to balance the sulfurs, 1 on each side, we're good. Then I'm going to balance the oxygens, 3 on the left, 1 on the right, add a water to the reactants side. Then I'm going to balance the hydrogens. I just put 2 with that water, so I'll put 2 on the product side. Then I'm going to balance the electrons. I've got a total of negative 2 over here, a total of 0 on the other side. So in order to make negative 2 equal to 0, I'll put 2 electrons. That is my entire oxidation half reaction. It's good, it's done. Let's look at reduction. We have MnO4 minus on the left and MnO2 on the right. First thing is manganese. 1 on the left, 1 on the right, manganese, good. Then oxygen. 4 on the left, 2 on the right means add 2 waters. 2 waters has 4 hydrogens in it, so 4 hydrogens get to be added to the other side. As far as charge is concerned, 4 pluses and a minus is a total of 3 plus on the left, and nothing on the right means I need 3 electrons. Three electrons, and an MnO4 minus and 4 pluses is a total of 0, so we have 0 and 0. Next thing we're going to do is multiply to make the number of electrons equal. So now we're going to have to multiply this entire reaction by 2 and this entire reaction by 3. So we're going to distribute that 3 in and distribute that 2 in. At this point, I highly recommend rewriting what you have because it's going to start to get a lot looking like chicken scratch and it'll be really hard to tell what's going on. So I'll put a 3 here, 3, 3, 6, 6, 6, 4 times 2 is 8, 2, 2, and 4. Rewrite it now after you've got that because we're going to start to cancel more things and it's going to start to look weird. So now that you've rewritten what you have, it should be easier to see that the 6 electrons are going to cancel. And even before you start adding the reactions together, if you've rewritten what you have, you should be able to see the hydrogens and the waters that will cancel. We have 3 waters on the left and 4 waters on the right. So all 3 of these are going to go, and all but 1 of those are going to go. For the hydrogens, 8 and 6, all 6 of these are going to go, and all but 2 of those are going to go. So that when I add my reactions together, I won't then have to cancel another time. If you didn't rewrite here, you will definitely need to rewrite before you start canceling hydrogens and waters, because it's really easy to get lost in all these numbers. So I'll end up having 3SO3 minus 2, and 2H plus, and 2MnO4 minus, and on the right-hand side, 3SO4 minus 2, and 2MnO2, and just 1 water. So that would be totally done if it were an acidic environment. But unfortunately, it's a basic environment. And basic means an excess of hydroxide, not hydronium, not H plus, OH minus. I just wrote OH plus. How silly. OH minus. So the way to fix that is to add the same number of hydroxides as you have hydrogens in the final reaction. So 2H pluses, we're just going to add in 2 hydroxides. But whatever you do to the left, you have to do to the right, so plus 2 hydroxides on the right. What that's going to do is cause these 2 hydrogens and 2 hydroxides to really be 2 waters. And on the right-hand side, on the product side, nothing changes. Since you did that, and you had a water over here, now this water is going to cancel, and one of those waters is going to cancel, and we're going to rewrite the whole reaction. What's on the left stays on the left. 3SO3 minus 2, and only 1 water, and 2MnO4 minus. On the right-hand side, 3SO4 minus 2, and 2MnO2, and no waters, and 2 hydroxides. That should be balanced and basic. Let's check. 3 sulfurs, 3 sulfurs. Let's go with 9 plus 1 plus 8. That's 9 plus 9 is 18 oxygens on the left. 3 times 4 is 12. Plus 4 is 16. Plus 2 is 17, 18. 18 oxygens on the right. For the hydrogens, 2 and 2. We're good. Manganese, 2 and 2. We're good. Oxygens are good. Sulfurs are good. All of the atoms themselves are good. Now all we need to do is cross our fingers that the charge is canceled like they should. 3 negative 2s is a total of negative 6. And 2 negatives minus another 2, that's a total of negative 8 on the reactant side. Over here we have 3 negative 2s, that's a total of negative 6, plus 2 negative 1s, that's negative 2 more, which is a total of negative 8 on the product side. Hey, negative 8 equals negative 8, and this reaction is balanced. Woo! Now you know how to balance redox half reactions, or redox reactions using the half reaction method. I know this seems a little complicated, but once you've done it 100 times, it actually gets pretty simple. I hope I see you again next time for precipitation reactions.